n1, and this can be also written as mu2 upon mu1. In sometimes some books it is also written as n2 upon n1. So here we can say that the n1 sine I must be equal to n2 sine r. So here we can conclude that n into sine theta equal to constant. If there are more than one mediums are given in such a way, suppose there are more than one mediums are present, say this medium is having refractive index n1, n2, n3, and n4, and again suppose this is the medium n1. And suppose ray of light is coming in this way, this is the normal. All the normals are parallel to each other. Then what we observed that what is happening here, the light ray that is emerging from the final surface makes same angle, the angle made by the incoming ray. If this angle is theta, this angle is also theta. This can be observed by using the Snell law. Hey, next.
Okay, Pankaj sir, you are live now.
Okay, sir.
Huh?
Thank you, sir. Okay, sir. That is the next concept. That is the application of the Snell law, concept of the apparent depth. What is happening generally? If I am talking about, suppose if some object is inside any liquid, and say the object is here, and suppose we want to see the given object, and the observer is present, suppose in another medium air, and object is placed in another medium water. Then what is happening? We can't see object its original position because of the reflection. And what is happening here? If we consider the ray is coming from the object in this direction, we can say this is the case of the normal incidence and light is going to the directly in our eye. But if we consider, suppose this is some another ray that is striking on this surface, we can say this is the boundary surface for the two medium, and say this is the medium of water. Say this medium is N1 and say this medium is N2. So here the phenomena of reflection is occur, and we know that the light is traveling from the water to air. We can say light is moving away from the normal. We can say light is moving in this way, right? We can say if light is moving away from the normal, so how we can got the image of this object that is inside the water? We can say if light is moving in this way, and if we extend backward direction, because in forward direction these two rays are in diverging nature, they never meet in this direction. So if we extend this ray in backward direction, this will meet at a given point. We can say this point is I. So here we observe the image of object O. So we know that if the original height of object from the free surface of liquid, that is HO, and this is the final height of object which is seen by observer, So in this case, we can say we can't see actual depth of the observer. We see some other depth, that is, we can say there is a shift involved in this type of problem. And what is the value of shift? How this shift is given here? And what is, you want to write down what is the image distance from the plane surface? This can be written as height of object, and this can be also written as n incident ray upon n reflected ray. We have to very much clear about what is the n1. Yeah, ni, that tells about that refractive index of that medium, where incident ray is present. We can say this is the nothing but refractive index. This is the refractive index of the medium where incident ray is present. We can say this is our refractive index of medium where incident ray. Here is incident ray. And if we talk about the NR, we can say the refractive index of the medium where refraction is occur. We can say this is the refractive index of the medium where the refraction is occur. So in this manner, we can find out the height of image if height of object is given. Suppose if this is the air, so we can say if this is the air, so in this case we can say that here we can write down the refractive index of this medium is 1, refractive index of this medium we say n, where height of image, this can be written as height of object divide over mu upon 1 or n upon 1, whatever we have taken here, we can say this can be written as h naught upon n. And if conceptually we think, we can say that the height of image in this case that is the lesser than, height of image is lesser than the height of object. So we can say if this value is lesser than height of object and refractive index is always greater than equal to 1. So this is ultimately height of object is divided over n. In the second case, when observer is present inside some denser medium and object is placed at suppose in air or some rarer medium, then what is happening in the second case? We talk about the second case. In second case, what is happening? Suppose in this case, our observer is present in this medium and object is placed, suppose in a denser medium. So in this case, what is happening? In this case, the height of image from the free surface that is greater than the height of object. In this case, the value will come like this, refractive index into h naught. In this case, if we draw the ray diagram, what we observe that the image distance from the free surface is greater than the object distance. So in this manner, if we find out what is the shift involved here, shift means that is what is the distance between height of object and height of image. So we can say that this value is nothing but h naught minus h naught upon mu, and we can write down h naught minus 1 by u. So this is the value of the shift. This is the value of the shift. Again, in the case of the lateral shift, what is the lateral shift? If incident ray is this is the incident ray that is striking on the surface of a glass, we consider, if we draw a normal here, this is the angle of incidence. And we know that because of the law of refraction, the light ray is bending toward the normal. We consider the light ray is coming from some rarer medium air. So here we apply the Snell law, and according to Snell law, we can write down that sine I upon sine R is nothing but if we consider the refractive index of the glass material is n, we can write down this n upon 1. That is the n a equal to 1. Again, what is happening? This ray is striking another surface, that is the boundary surface between the glass and air. Here light is going from the denser medium to rarer medium. So it is bent away from the normal. And if we say this angle is A, say this angle is B, then what is the shift involved here? What is the meaning of the shift? If we extend incident ray, and this is our emergent ray, then what is the lateral deviation between the ray, that is known as the lateral shift. We can say this is our shift. If we consider the thickness of glass is T, if we consider the thickness of glass is the T, and we write down the Snell law for both the surface at surface 1 and surface 2, then we can find out the value of lateral shift. That lateral shift, that is also represented by x here. We can say this shift is written in this manner: t sine I minus r divide over cos r, and this result is very easily we will get after applying the Snell law at both the surface and applying some geometry. So here what we observed that the lateral shift x, this can be proportional to thickness of the glass slab, as well as this x is proportional to, we can say that, angle of incidence, that is I. So here we can say that here x is proportional to sine I minus r divide over cos r. This is the lateral shift. The next, that is the very important application of the Snell's law, that TIR, or total internal reflection. In the case of total internal reflection, what is observed whenever light is traveling from denser medium to rarer medium, then we know that the light is bending, that move away from the north. We know that if light is moving from the denser medium to rarer medium, light is moving away from the normal. At a given angle theta, if the angle of refraction is theta 2, so we can say that if this is the denser medium and we consider the refractive index of this medium, suppose if we consider refractive index of this medium is n1 and refractive index of this medium is n2, so for theta 1, we can say the angle of refraction is theta 2. As we increase the value of theta, we can say that the angle of refraction is also increases, because using sine law we can write down this sine theta 1 divide over sine theta 2. In this case, this can be written as n2 upon n1. So here, if we increase the value of theta 1, we have to increase value of theta 2 is also increases. Then what will observe if we increase the value of incidence, then value of angle of reflection is also increases. And for a given specific angle of incidence, what we observed that the angle of refraction will become 90 degree. At some specific angle of incidence, what we observed, the angle of refraction will become 90 degree. If further we increase the angle of incidence, that what will happen? The ray reflected back in the same medium, and we can say that after that reflection phenomena is occur. So this is the boundary condition, or we can say this is the critical condition where refraction is occur. For a given angle, that is the special angle theta c, at theta equal to theta c, where r equal to 90 degree, this is the condition, we can say this is the critical condition. And in this condition, what we observed, we can say that if you put this value in the Snell law, we can say that here this sine theta c upon sine theta 2, in place of theta 2 or angle r, we can say we have to put angle 90, and this will become n2 upon n1. So here we can say that the sine theta c is nothing but, we can say, n2 upon n1. If n1 is refractive index of the denser medium, and most of the time the rarer medium, that is air, is present in rarer medium. So if we consider here that n2 is rarer medium and that is air, so we can put the refractive index of n2. So in this manner, what is the critical angle? We can write down in this equation that 1 upon n. Here we can also write down the theta c in this manner, sine inverse 1 by n. So there are two basically conditions What is the condition for TIR? Light is traveling from the denser medium to rarer medium. This is the very first condition. And the angle must be greater than critical angle. If our theta is greater than theta c, then we can say that this light is reflected back into same medium. Then we have to must follow the law of reflection. We can say if this angle theta is greater than angle critical angle of incidence, then we can say total internal reflection is occur. There are lot of example that is governed by total internal reflection. If I talk about the mirage, either optical fiber, either in the billions of the diamond, otherwise that is the infringement, that is application of the TIR. So here, if we consider the case, this is the case of the optical fiber. What is happening in the optical fiber? When light is incidence, light is entering in a optical fiber once, then the material of cladding and the outer surface is such that the internal medium is acting like as a denser medium as compared to this medium that is acting like as a rarer medium. This is designed in such a way the internal medium is denser as compared to this medium. So here light is traveling in multiple reflection and that is the TIR occur. We can say once light is entering into this tube, this is not going to outside in this way and multiple reflection. Because of the multiple reflection, we can say that this is the concept of the optical fiber. In this way, we can say information is transferred in the way of the light. So basically, this is the application of the TIR. The next topic, that is the refraction from the curved surface. Firstly, we have to cover the refraction through plane surface, and this is the second segment where we have to go through refraction from the curved surface. What is happening here? Suppose if we consider a point object, that is point object is kept at a distance u. Say this is the pole of the curved surface. Suppose in just similar to the concave and convex surface, we consider a surface here, right? And this is the symmetric point. We can say this symmetric point is P, and that is the part of a spherical glass. We can say it must have some center in this direction, and that is known as the center of curvature. This is the center of curvature C, right? So this is the center of curvature of this curved surface. And the line joining pole and center of curvature is known as the principal axis. We can say this is our principal axis. If some object is placed here and we know that the ray is coming from the object, so if we incidence one ray on this curved surface, then what we have to do? We have to draw a normal so that we can form the image of this object and we can apply the Snell law. So we know that this is the center, and in a spherical surface, normal is always passing through center. So we can draw our normal in this direction. This is our normal. And say the ray is coming from this object and object is kept at any medium. And we can say that the refractive index is medium is N1. And this is the medium that inside the spherical surface, we can say this is the medium that is N2. And if we consider that the N2 is greater than N1, we can say that the N1 is rarer medium and N2 is denser medium. And we already know that when light is traveling from rarer medium to denser medium, so we can say that in this case, light is bending towards the normal. So if we draw original path of the light, if there is no refraction occur, then light is going in such a way, but there is curved surface in between. we can say that the light is bending towards the normal. So in this way, light is bending, and we can say that if one ray consider that is follow along the principal axis, and this is the second ray, and if we consider two ray, and these two ray is the reflected ray at a point on principal axis where two ray are intersected to each other, we can say that this is our image. So this is the image of the object O, and we already know that all the distance is measured from the pole only, and we already taken in sign convention that the direction of incident the direction of incident ray, whatever distance is measured in the direction of incident ray, that is taken positive. The direction that is measured opposite to direction of incident ray, that is taken negative. We can say that this distance of object from the pole, and that is measured opposite to the direction of incident ray, we can say this distance we have to take in negative here, and this is the distance of image from the pole. This is the distance, we can say this distance is V. The center and the distance between the pole, we can say this distance is R. Right. Whenever we consider all the aspects of ray optics, we consider only paraxial ray. And what is happening in the case of paraxial ray, the angle made by the paraxial ray from the principal axis, that is very small. So in this case, what is happening and what we can consider, if angle is very small, if angle is very small, so we can take the approximation. Whenever tan alpha is come, we can consider tan alpha equal to alpha, tan beta equal to beta, sin alpha equal to also alpha. This approximation is considered in case of ray optics. If we consider the angle made by the incident ray from the principal axis, that is the alpha, angle made by the refracted ray from the optical axis beta, and the angle made by the normal from the principal axis, that is the gamma. So in this way, we can say this is the point where law of refraction is applicable. So we can say this is our incident ray, this is our normal, so this angle is I. This is our refracted ray, this is our normal, so this is angle R. And if we apply sine law here, we can say that is the Snell law here. We can write down that sine I upon sine R, this must be equal to N2 upon N1, right? Guys, we know that if angle is very small, we can say that N1I equal to N2R, right? Here we have to develop a relationship, and we have to keep in mind whenever we have to develop a relationship, what is the relationship? That is N2. What is the relationship here? That is N2 upon V minus N1 upon U equal to N2 minus N1 upon R. This is the relationship we have to derive. Then we have to keep in mind in the final result, we only want N1, N2, V, U, and R. So we have to say that we have to eliminate I and R from here. Say this is the equation number 1, right? If we use some basic geometry here, and if we consider that this curved surface having very small aperture, then we consider point M and P is the very close. So in this case, we can consider the point P and M that is very close to each other. Then we have to find out value I and R in terms of alpha, beta, and gamma. Then establish a relationship in such that we can eliminate I and R, and we can get this result. This is the required result, that N2 upon V minus N1 upon U equal to N2 minus N1 upon R, where N2 is the refractive index. N2 is the refractive index where the image is formed. N1 is the refractive index where object is kept. U is the that is the coordinate of, we can say that is the coordinate of object. V is the coordinate of image, and R is, we can say this is the radius of curvature. By using this law, we can also derive the lens maker's formula. That is the again very important formula. That is the lens maker's formula. Lens maker's formula. According to lens maker's formula, what we conclude that if we consider that this is our first surface, this is acting like as a first refracting surface. This is acting like as the second refracting surface. And if we consider the first refraction from the first surface, then we can write down the formula. That is the formula from the curved surfaces from the first surface, and we can write down this formula that N2 upon V minus N1 upon U equal to N2 minus N1 upon R. If we consider that the radius of curvature of the first surface is R1, refractive index where object is kept, we consider that is the N1, and the image is formed, that is the N2. So if we apply this formula for the first surface, say this is the first surface and this is the second surface. The image formed by the first surface, that is acting like as an object for the second surface. If we again apply this formula for the second surface, then we again get similar type of relation, and that something like as N2 by V minus N1 by U equal to N2 minus N1 upon R. Here we have to put the radius of curvature of this surface R2, and if we have to see where object is kept, that we have to take in as N1, and where image is formed, that we have to take in as N2. So after solving two equations for the surface 1 and surface 2, and finally we get very important formula, and we already study the formula. What is the lens formula? That 1 by V minus 1 by U equal to 1 by F. This is the lens formula, and here what we know, what we will get after solving the equation for two surfaces, that NL upon NS minus 1, 1 upon R1 minus 1 upon R2. This is the again very important formula we will get after solving the equation for curved surface for both the surfaces. And here we have to very careful while writing the NL and NS. What is the NL? NL is the refractive index of lens. NS is the refractive index of the surrounding medium where lens is placed. We can say that NS is the refractive index of surrounding medium where lens is placed. So in this manner we can calculate the focal length. Guys, if there a convex lens is given, so we can say that if convex lens is given, suppose in this way, and this is, if we can consider that this is equiconvex lens, so we can say if this is the equiconvex lens, then we can consider that R1 equal to R2 here. We know that this is the R1 of first surface, this is the R2 of second surface. Then what will happening here, if this lens is placed in air and the refractive index of medium of lens is N, then focal length of this lens we can write down here N minus 1. We know that the refractive index of air is 1. That radius of curvature of the first surface, we can say this is 1 upon R1. And radius of curvature of second surface, if we write down, that is minus 1 upon R2. Why minus? If we consider that object is placed somewhere here, we can say this is the direction of incident ray, and whatever distance measured in this direction we have to consider positive, and whatever direction measured in this way we have to take a negative. And this is the common for the both the surfaces, and this point of lens is known as the optical center, and all the distance is measured from the optical center. In the case of lens, we can say that in the case of R2 is lie in somewhere, we have to put negative sign here. That's why we can say this will become n minus 1, that 1 upon R1 plus 1 upon R2. If R1 equal to R2, in the case of equiconvex, we can say that this will become n minus 1, 2 upon R. So this is the formula of the focal length in the case of equiconvex lens. The same concept is also applicable for the in the case of equiconcave lens. And one the most important thing, when the lens is present in air, we can say the focal length of this convex lens is the secondary focus is considered at the principal focus, and secondary focus is light in the right side in the direction of incident ray, and we can define the secondary focus whenever the light is coming parallel to principal axis, and after the refraction the ray will meet at a given point and the principal axis. That point is known as the secondary focus, and the secondary focus is considered at the main focus in the convex lens. And we can say in case of convex lens, focal length is positive. If lens is placed in air, I am not talking about lens is submerged into any medium. Lens is submerged into any medium, that is depending upon the situation, what is the refractive index of the surrounding medium, then the focal length is also going to be changed. But if I am talking about general lens is present in air, then the focal length of convex lens is positive and the focal length of the concave lens is negative. In the concave lens, that is the focus is, we can say that if the ray is coming from, we can say parallel to principal axis, and after refraction the ray is diverging to each other. So we can say in this case we will not get real focus, then we have to trace the ray in backward direction, and they appearing to meet at a given point on the principal axis, and that is the primary focus is the major focus in the case of the concave lens, and we can say this focal length is the negative in the case of the concave lens. So in this manner, we can conclude that in general, focal length of convex lens is positive, focal length of concave lens is negative, and the convex lens is also known as the converging type of lens because it want to converge the ray. We can say this is the converging nature, and the concave lens is the diverging nature. This is the diverging nature, right? That is next one is the magnification in the lens. What is the magnification? As we discussed magnification in mirror also. What ultimately magnification tells the size of image as compared to the size of object. Okay, here if we write down the lens equation, lens formula, we can say 1 by f equal to 1 by v minus 1 by u. This is the formula of the lens, and if we want to find out the magnification, so we can say magnification is nothing but that is the size of image upon size of object, and this result in the case of lens is v upon u. What is the v here? V is the image coordinate and u is the object coordinate. We can say v is our image coordinate and u is our object coordinate. So sometimes magnification is given, object distance is also given, and we have to find out the image distance. So by using this formula, we can easily find the image distance. And what is happening here? Sometimes in this type of questions, guys, this type of question, the convex lens property is just similar to the concave mirror. We can say in most of the cases, except one case when object is kept between primary focus and optical center, then the convex lens form, that is the we can say that form virtual image and erect image, but except this case, convex lens is always form real image. Okay, that is the similar to concave mirror. And if we talking about the case of the concave lens, so concave lens always form virtual image. We have to keep this thing also in our mind for talking about this. This is the formula. We can say 1 upon V minus 1 upon U. We can say this is 1 upon V and this is the 1 upon U. Next one is the cutting of lens. Sometimes we cut the lens. If we cut the lens, there are two possibilities. Either we cut the lens that a line parallel to principal axis are perpendicular to principal axis. Then what is happening? If we cut the lens in this manner, then what is happening? The power and the focal of lens is not going to be changed, and the image position is also unaffected. We can say in this case, image position is also unaffected, right? But in this case, why image position is unaffected? Because we know that if we apply the formula 1 by f equal to 1 by v minus 1 by u, object distance is not going to be changed. Focal length is remains same. So we can say the object that image distance is unaffected, but the intensity of, we can say the intensity of image is decreases. Intensity of image decreases. But in the same, if we consider this case, if we cut a line that is perpendicular to, we can say principal axis, and this type of cutting of lens, we can consider that this is a separate plano convex lens, and this is also a plano convex lens. And if we apply the formula in this lens, what we observe that the focal length will become 2 times. In this case, focal length is become 2 times. And we know that if we apply this formula 1 by f equal to n, that is the lens maker formula, nl upon ns minus 1, that is 1 upon r1 minus 1 upon r2, right? If we consider that the lens is kept in a air, we can say that ns equal to 1 and 1 upon f, that is n minus 1 equal to, and the both the, if we consider that this is become 1 upon r1 minus 1 upon r2, right? If we consider that if R1 and R2 is same in this case, so what we can say that 1 upon f, that n minus 1 equal to 2 upon r. If we consider for a plano convex lens, suppose this is our plano convex lens, and if we want to write down the focal length formula in this case, we can say this is the 1 upon f1. We can say n minus 1, that is 1 upon r, and we know that this is the plane surface and the radius of the plane surface is infinite. This will become 1 upon r. So in this manner, what we can say that 1 upon f1, this can be written as, guys, this can be written as, we can say that this can be written as nothing but 2 upon f. And in this manner, we can say that, guys, f1 is nothing but, what is the value of f1? If you want to write down the value of f1 here, so how we can write down the value of f1 here? After comparing these two equations, say this is the equation number 1 and this is the equation number 2, we can say that the focus is, new focus is nothing but 2 times of the first focus. This is the become 2 times of the first focus. So in this manner, we can say that this relation is valid. And after applying the formula, we can say that what is the exact relationship power and focus. If we define the power of a lens, so power of a lens is defined at 1 upon focal length in meter, where power is represented in diopter. As we consider converging lens, that focal length is positive, so we can say that power is positive for converging lens, where power is positive for the converging lens. And if we consider that focal length is negative, so power is also negative, and this is valid for the diverging lens. This is valid for the diverging lens. Okay. If lenses are kept very close to each other, if we consider two situations, suppose this is the lens L1 and this is the lens L2, and both the lens place kept close, very close to each other. So what we can say that if the power of lens 1 is the P1, power of lens L2 is the P2, then the net power we can say that if both the lens having same nature, that is the convergent type, 1 P net equal to 1 upon P1 plus P2. So we can say 1 upon F net is also written in this manner, 1 upon F1 plus 1 upon F2. If we consider that the two lenses having the opposite characteristics, one is the convex lens and suppose another is the concave lens. We can say that this lens having converging type of characteristics, this lens having the divergent type of characteristics. In this case, we can write down the P net is nothing but P1 minus P2, and we can say that F net is nothing but 1 upon F1 minus 1 upon F2. So this type of concept is applied whenever lens is kept very close to each other. We can directly apply this type of concept whenever the question asks the lens is very close kept to each other. Another concept that is the silvering of lens. What is the silvering of lens? If we are talking about the silvering of lens, sometimes what happens, we silvered one surface of the lens. If we consider that is suppose this is our convex lens, and if we silvered this surface of lens, then what is happening? If a ray is coming in this direction, so firstly refraction will occur, and we can say that after refraction the ray is strike on this surface. Because of the second surface is also acting like as a concave mirror, we can say that here the finally reflection is occur. If you want to study the effect of both combined lens and mirror, we can separate these two. This is our lens and this is our mirror. So what we can say that firstly, if we want to write down, firstly it is refraction from this lens and then refraction from mirror. If you want to write down the equivalent power, so firstly what is happening? Firstly that is refraction from the lens, we can say that this is the power of lens. Then what is happening? That is the refraction from the mirror, we can say power of mirror. Then again refraction from the mirror lens, we can say power of lens. So in this manner, we can say that P equivalent, that PL 2PL plus PM. But what we observe here, this is the power of mirror, and power of mirror we can consider that negative, because concave mirror having the negative characteristics, and the final ray is moving because of the reflection. We can see this is also behaving like a mirror. We can see the characteristics of this power. This can be also written as minus 1 upon F equivalent equal to 2 times 1 upon FL. And this will also written as 1 upon mirror. This is the equation whenever silvering of lens is given, and we can apply this formula. Let's move for the next segment, that is the prism. If we are talking about the prism, what is happening in the case of the prism? This is very much clear. The prism is that is the bounded surface, and we can say that this is the triangular surface, triangular, and this is a, we can say this is a square type of rectangular surface. So there is the rectangular surface and the triangular surface is present. And when ray of light, that is the white light incident on the fridge, then what is happening after when ray is emerging from the fridge, it will splitting its seven colors. As we know that in white light, that is the seven colors, that white light made from the seven colors, that is splitting of light is occur, and this phenomena of splitting of light is known as the dispersion. So by prism, we know that this type of phenomena is happen if we study that is the front surface, that is the front view of this prism. And if we consider that the light is coming in this way, we can say this is our incident ray. And if you want to draw a normal here, we can say if you consider the refractive index of the prism is n, and the prism is placed in a medium, we can say if this is the air, and light is coming from air to a medium of prism. We can say light is bending toward the normal. We can say this is the path after the reflection of the first surface. If we again draw normal here, this is the normal for the second surface. In this case, light is moving away from the normal because light is traveling from denser medium to rarer medium. So we can say this is our emergent ray. This is our incident ray. And if we say this angle is I, this angle is R1, this angle is R2, and the final angle made by emergent ray with normal is A, and the angle of prism that is given as A. If A is the, that is angle of prism. So here it is very quite obvious that is refraction is occur at the two surfaces of prism. So we can apply the Snell law at the two surfaces. Say this is the surface 1 and this is the surface 2. If we apply Snell law, if we apply Snell's law at surface 1, then what we can say that here by Snell law sine I upon sine R1, this must be equal to that refractive index of medium 2, that is n, and refractive index of medium 1, that is 1. So here, if you want to find out what is the refractive index of prism, we can directly find out by putting the value of I and R1, that is sine I upon sine R1. Say this is the equation number 1. If you want to apply the law of refraction and the Snell law at the second surface, we can say that again we apply Snell's law at surface 2. So we can say that in this surface, this angle R2 is acting like as a angle of incidence on this surface. We can say that sine R2 upon sine E, this must be equal to 1 upon, we can say that 1 upon n. So here we can also apply the Snell law in this manner. Okay. And whatever apply the geometry here, what we observe here that R1 plus R2 equal to A. That is the very important result by applying the geometry, because we know that this is a triangle and the sum of angles of triangle is nothing but 180 degree. So in this manner, we can write down R1 plus R2 equal to A. And one more thing, if we want to draw the deviation of incident ray, we can say if incident ray is going along its original path, this is the original path of incident ray, this is the emergent ray. The angle made by incident ray and emergent ray is known as the, we show this some other different colors. So if you want to show this some different color, so we can say that this is nothing but this is the angle of deviation. And in this case, angle of deviation is written I plus E minus A. This is the very important equation. We can say this equation is also we will get after applying some simple geometry here. So this is the equation number 2 and this is the equation number 1. And one more thing, If we apply the condition for minimum deviation, condition for minimum deviation, what is the condition for minimum deviation? So we can say angle I must be equal to E, angle R1 equal to angle R2, and the light that is parallel to the base, that light moving after the reflection to our surface parallel to the base. If we put this value, so we can say that we have R1 plus R2 equal to A. If R1 equal to R2, if R1 equal to R2 equal to R, so we can say R is nothing but A by 2, and angle of deviation that can be written I plus E minus A. And if we apply the condition I equal to E, this is the condition for minimum deviation, then this minimum deviation, this can be written as I plus I, that 2I minus A. And if we put the value of I here, this can be written as A del minimum by 2. So here we can get the value of I and R. So in this manner, if we put the value in equation number 1, that N equal to sine I upon sine R1. So we can put this value here. In the place of I, we can put A plus delta minimum upon 2 and divide over sine R1 in place of R1 and R2, that is equal to R sine A by 2. This is nothing but this is the refractive index of our prism material, sine A plus del minimum by 2 divide over sine A by 2. That is the very important formula, and that is very important topic regarding JEE NEET and board also. Sometimes we have to draw the graph between angle of deviation and angle of incidence. So we will get something like this type of graph, and in this graph what we will get that whenever the angle of incidence is increases, then we will get one angle is such that where angle I equal to angle E, then the angle of deviation will become minimum, and this is the minimum angle of deviation. This will occur for I equal to E. We can say that it's a situation where I equal to E. Right? Let's move for thin prism. What is the thin prism? Whenever the angle of prism is very small, say this is the angle of prism. If generally this angle is less than equal to 6 degree, we can say this is the case of the thin prism. And in thin prism, if we write down the formula of the refractive index of the prism, that n equal to sine delta minimum by 2 divide over sine A by 2. If we say if angle is very small, in this case we can write down sine theta must be equal to theta. So in this manner we can say n can be written as A plus del minimum by 2 divide over A by 2. After solving this, we can say that this can be written as n into A plus del minimum. Here, if we want to write down the value of del minimum, this can be written as n minus 1 into A. This is again very important result. And here what we concluded is that the deviation is proportional to refractive index. That is very important result. That angle of deviation is proportional to refractive index of prism material, right? So this is the very important formula. One another observation from the Cauchy formula. And what is the Cauchy formula? So according to Cauchy formula, what Cauchy concluded that refractive index, this can be written as A plus B upon lambda square and some higher power of lambda in this manner. So we can say that according to Cauchy formula, one observation that n is inversely proportional to lambda also. n is inversely proportional to lambda also. So in this manner, what we conclude that the delta, that angle of deviation is proportional to n, and n is proportional to 1 upon lambda. So we can say that the angle of deviation is that is inversely proportional to lambda. This is very important regarding the phase, because we know that when light ray is splitting its 7 parts, with each color having different refractive index. So different refractive index because different wavelengths. So different angle of deviation. So the ray having maximum, yeah, we can say maximum wavelength that must possess minimum angle of deviation. So if we are talking about in big cure, that is the 7 color of light, and we know that this is the increasing order of wavelength. Red color having the maximum wavelength and violet color having the minimum wavelength. So according to this, we can say that which one having the maximum wavelength, that must possess minimum angle of deviation. So we can say in this case red minimum deviation, and in the case of violet we can say maximum angle of deviation that is occur. So we can say that this is our pressure and light is traveling in this manner, and after the refraction, if you consider this ray is breaking in its 7 colors, the ray is breaking in its 7 colors. We can say that one, the ray which one is suffer most deviation, that is the violet ray, and the least one is the that is the red color. We can say in this manner. So here what we can say that the red color having least deviated and the violet ray has the maximum deviation. So here this is what we observed in our formula, that delta, that is inversely proportional to 1 upon lambda, that is clear from this diagram. So this type of pattern is observed generally from the prism. That is the another concept, that is what is the angular dispersion. If you want to define the angular dispersion, this particularly this type of phenomena, that is splitting of rays known as the dispersion, we can say that which ray deviated most, that is the violet color, and which ray that is deviated minimum value of angle of deviation, that is the red. If we find out the difference between this is known as our angular dispersion, and this angular dispersion is represented by theta. We know that in the case of in prism, we can write down the angle of deviation in the term of refractive index. We can write down NB minus 1 into A minus NR minus 1 into A. In this case, we can also say that this will become NB minus NR into A. This is nothing but our angular dispersion. So angular dispersion, this can be NB minus NR into A. Second one is the average deviation. So whenever average deviation is asked, we just find out the mean deviation is also known as the average deviation, that is the yellow color deviation. So in this, we have interested to find out that is the deviation of the yellow color, that can be written as NY minus 1 into A. This is the known as the